Hello and welcome back to Introductory Electromancy. Today we continue building the transcranial direct current stimulator, transcranial direct current stimulation device, tDCS device, which can be used to run a current through your brain in order to produce a variety of different effects depending on where the electrodes are placed. This device follows the safety protocols first established by Walter Paulus at the University of Göttingen, which specify a current of no more than 2 milliamps for no more than 20 minutes at a session, with electrodes that have a minimum surface area of 25 square centimeters, such as these. Now, we have calculated the circuit, we breadboarded the circuit, we tested the breadboarded circuit, and as a result of individual component variations, the output current was a little bit lower than the intended design value, so we added a resistor in parallel with one of our other resistors to decrease its value based on the parallel resistor equation. We found that this caused our output current to become 1.96 milliamps at the nominal supply value, nominal supply voltage value, assuming the battery's output 5 volts, or 9 volts. Good heavens. In any case, the value of this circuit is that it is a current regulator, so it will provide about 2 milliamps across a wide range of supply voltages. We can turn the supply down, and it will still provide about 2 milliamps, or we could turn it all the way up, and it will still provide about 2 milliamps. The reason this is important is because 9-volt batteries don't actually always give you 9 volts. And it depends on the battery chemistry. So I would recommend the PowerStream Battery Chemistry FAQ for you, dear viewer, if you wish to learn more about every single type of battery currently in production and some that are no longer in production. This circuit will be powered with common Leclanché cells or alkaline batteries. And the important thing to note here is this graph, which shows the cell voltage under various loads. It starts off at about 1.6 volts per cell, then goes down, then stays relatively constant with a gradual slope downward. The shape of this slope, called the discharge curve, varies depending on battery chemistry. I'll link the battery FAQ in the description. I know you have nothing better to do with your time than learn about all of the different battery chemistries that we use as a species in order to power our devices. So, following the prototyping steps, draw or find your schematic, calculate the values of the components in your schematic, ensuring that they do not exceed the maximum power dissipation for the component. Build the schematic on a breadboard. Test the output of the schematic in real life. Make adjustments as needed. Then you can transfer the components from the breadboard to a perf board, perforated board, which has small annular copper pads that are not connected but provide a convenient point to solder your components to. Now, I have not decided if I actually want this to fit in some sort of project enclosure, but in the interest of completeness, I wanted to show you one of the nice things about perf board is it's really easy to snap along these rows of holes. Having said that, I'm sure it will now go poorly in real life, but I'm a big believer in tempting fate. Why not? This works best if you put the board along the edge of something with a 90-degree angle, like a metal filing cabinet or a step. Hold one side with the palm of your hand, and then do a quick smack with the other palm of your other hand, which will tend to snap the board along these rows of holes. However, that is something of a challenge to set up, so I'm going to attempt to use pliers. Aha. And this will leave a rough edge where it was snapped. You can use sandpaper or rub it on concrete or brick, depending on the level of sophistication of your technical setup, dear viewer. So, now we have our lovely little piece of circuit board that could, in principle, fit into this enclosure if we so desired. We can place our switch. Guess I'm going to make it so that if it were put in here, the switch would protrude out this side. I do not think I will actually be putting it in there, dear viewer. I could, but I don't know if it's really necessary for this explanation or helpful. I'm pretty sure you know how to put things in a box. At least, I hope you do. You probably shouldn't be building your own neuromodulation hardware if you don't know how to put things in a box. No offense. So, real life practical assembly. Fun times. I spent a fair amount of time attempting to finesse this switch into having all of its little pins fit the 0.1 inch spacing on this board, which they do not by default. It has its own thing going on, which for a human or organism would be a wonderful display of individuality. For an electronic component, it can be something of a challenge. But that is about right. Not exactly right. About right. All right. So now we can solder. And solder we shall. I'm going to be using the TS100 soldering iron and SN100C alloy with an NC601 flux core, 0.032 inch diameter. It's lead-free solder. Don't use leaded solder. We're in the future. Why would you voluntarily subject yourself to potentially neurotoxic lead when it is not necessary? That would be foolish. The solder is actually the thing that holds up my phone in my wonderful, wonderful filming setup here. And the soldering iron has reached 350 Celsius. have to figure out a way to get you, dear viewer, closer to the action. Let's see how well that holds up. So this is our power switch. Happy little power switch. These pins should go all the way through the board. Because this switch doesn't quite align with this perf board, they do not. I hope that you, dear viewer, will be able to find a switch that does, or simply use an external one that has leads on it. Such as this switch here. Cleaning the oxide off of my soldering iron, reapplying solder to tin the iron tip, maybe. Tapping off any excess. All right, great. So this circuit uses 4 9-volt batteries in series. And we have here some 9-volt battery leads, which we can begin attaching to our board. The red, the plus of the 9-volt battery lead, is going to be going to the switch, as you can see from our schematic. However, it will not reach the switch. Could I place it next to it? Yes. Will I? No. It looks nicer this way. That's what I have to say. And now the black lead of that connector will go to the red lead of the next connector, beginning to form a series chain. So you see the wires are bent, so they are almost touching each other. This will be close enough for me to just reflow them together with solder. Trying to show you this process in a detailed manner because it might actually be helpful. Now, in the previous episode during breadboarding, I added a resistor to fudge the value of this resistor a little bit lower by adding a large resistor in parallel with it. I think I'm going to leave that out of the final version because in case anyone is following these instructions verbatim, I would rather you end up with an output of only 1.94 milliamps as opposed to going too high, running too much current through your brain, because the study that I referenced, which showed that this could improve memorization and learning, actually only used an output current of 1 milliamp, which you could achieve with this device simply by adding another copy of this 105/60 ohm resistor in series with the other two, which would double the resistance here, and then because I equals V over R, doubling R cuts I in half for a constant V. But I want to verify the output current one last time before I assemble this. And I see 1.90 milliamps, which is low by 5%. Now that's with only 30.82 volts supply. With 9 volt batteries, when they're full, you can expect up to 40, which would get you up to maybe 1.92, 1.93 with this circuit. The output current should be relatively insensitive to changes in voltage, which is good because this circuit is a constant current source. So, isn't that nice? Now, because there are 4 9-volt batteries in series, we simply keep attaching more of them. The happy little 9-volt batteries. Plugging the leads in. Bending the leads over. Bending the leads makes it so that the component stays in place, which is important because if it does not, then you cannot reliably connect to it. If it's wiggling all over. This is not showing up very well on camera. My soldering iron tip has already become darkened with oxides, which will diminish its performance. Luckily, this is a pretty simple and forgiving circuit to build. I could have cherry-picked better components when I was first building this, instead of just grabbing components and then breadboarding them and recording the result, which would give the impression that it should be exactly 2 milliamps. It's probably better that I show you the realistic outcome of it being 5% low, because that's more reflective of what you'll run into in the real world. After all of the resistors are rated to plus or minus 5%, so it would follow naturally that a device that depends on them to regulate current would also be only accurate to within plus or minus 5%. Now, as constructed, this circuit has a problem, and that problem is right here. These two terminals are shorted. Shorted by a blob of solder, which I have now removed. It's easiest to find unintended shorts in a circuit with some sort of backlight, because then it becomes very obvious when there are gaps, because for the most part this FR4 circuit board material is translucent. So now we have our 4 9-volt battery terminals, and now we can talk about another practical real-life thing: durability. The way this circuit is built currently is fine electrically. Everything's wired up. A moderate strength tug does not remove the component, so the solder joint is good. But if you were to use this, the wires would break off. They'd break off right here. Repeated flexing will cause them to be destroyed. And this is because even though this is stranded wire is composed of a lot of tiny strands, and so it's easy to bend, flexible, withstands bending well. The ends of these were dipped in solder before they were shipped to me, and dipping your stranded wire in solder or allowing solder to wick up into your stranded wire effectively converts it to solid wire. Solid wire is fine, except if you bend it, it breaks. So you want stranded wire for applications where the leads will actually be bent in regular use. Solid wire is cheaper and could be used elsewhere. For very high frequencies, current only flows on the outside surface of the wire, and so you want extra fine stranded wire called Litz wire. But I've never actually had the opportunity to use it in real life. Perhaps someday. In any case, what you need is called a strain relief. Something that acts to prevent the wire from flexing at the point where it joins the board. And for a do-it-yourself project like this, hot glue will work fine. My hot glue gun will take a minute to warm up. For a commercial device, such as this power supply, which we dismembered earlier in this series, the strain relief you can see is molded onto the wire, and it interfaces with a little divot in the case, so that instead of bending at the case where it would break, the bending force is distributed over a longer length of wire and reduced in intensity at a specific point. So that prevents the wire from breaking off, or at least it makes it take longer for it to break off. So in this first project that we built, I thought that it would probably not be necessary to mention strain relief because it was supposed to be a very simple introduction. But you can see, even though this 9-volt battery lead is stranded wire, it's loaded up with solder here. So it's acting like it's solid. And 1, 2, 3, 4, 5. 16 bends, and it breaks. If this were a commercial product, that would be bad. If this were a project that you had built that you wanted to use for a long period of time, that would still be bad. So strain relief is really important. And another thing I should tell you while my hot glue gun is warming up is that you can put super glue over hot glue. Hot glue is convenient because it's reversible. You can peel it off without too much effort. Adding super glue over it does defeat that. But hot glue joints usually fail at the toe of the joint. If there were a blob of hot glue on this desk, it would begin peeling up right about there. And if you apply a bead of super glue around where the joint meets the substrate material, then it prevents that failure mode. It prevents it from peeling off as it would normally tend to do. And applying super glue over the surface of hot glue makes it so that the surface is hardened. So in some applications you might want to do that, but you should know that it's permanent and irreversible. Well, I mean, I guess you could mess around with a razor blade for a while. That would be one way to try and reverse it. But I wouldn't do it on something that you want to be able to undo. This is a relatively simple demo project, so I don't think I'm going to go to the trouble. But what I'm doing here is I'm making a strain relief so that the wire will not break off with repeated bending. as it is wont to do. Not as it wants to do, as it is wont to do. W-O-N-T. It's a different word. So this is not going to be a particularly beautiful set of wires, but it should hold up for a long period of time, at least longer than it would without the hot glue, which is the name of the game here. Increased durability. Spread the force that is applied to the wires over a wider area, etc., etc. So while this dries, the next step will be to connect this positive lead, the positive lead for the entire assembly of the 4 batteries. These 3 connections are internal. This positive lead will go to the switch. On this particular switch, these 2 terminals are mechanical, and it's a single pole double throw switch, so this middle pole will either get connected to the left or the right pad, depending on which way the switch is flipped. Because we're only using it as if it were a single pole, single throw switch, we just need to connect to the pole and one of the possible throw positions, leaving the other one open, and it will act as we want it to. So this is more or less dry. We're taking our global positive terminal, and I'm going to connect it to the center pole. I'm using solid wire, bell wire it's called, and I'm just going to be stripping it and using it as bare copper because that is easier in this application. Since I'm documenting this for posterity, try to be fancy with it. I need this wire to reach to the pole of the switch. Oh, that was largely invisible to you. That is unfortunate. Okay. Just move this all up a bit. So I bent the wire and simply set it on top of the board. Now I'm going to solder it to the center pole of the switch. And you can see it is soldered to the center pole terminal, but not to the 2 throws. The other 2 terminals that the center pole of the switch can switch to contacts, I suppose. There are usually 5 or 6 synonyms for every one of these terms, which can be confusing at first, but you get used to it over time. Now the other end of the wire is going to be connected to the positive terminal of the set of 4 batteries in series, which would really itself still just be called a battery, because battery means a series of cells and doesn't specify the number of cells in that series. So now we've gotten a ways into this. We've got our 4 batteries in series. You can see that the positive terminal of the whole set, the whole shebang, the entire enchilada, is connected to the center pole of this switch. One of the poles will leave open, the other one will be connected to supply the entire circuit. And I should note that I'm not including this trimming resistor because I don't want to lead you astray and cause you to run too much current through your brain, just the exact right amount.